Swayam Prabha. Digital India. Educated India.
So in this session, we will actually look at polynomial time algorithm for network flows. Right? This is due to Edmonds and Karp. So as you've seen, Ford-Fulkerson algorithm is a very generic algorithm for network flows, and the idea is to keep finding augmenting paths in residual networks, and as long as such path exists, push as much flow as possible through the augmenting path until there are no augmenting residual network has no paths. And we saw that if you are not careful about how we are doing finding these paths, then this running time can be essentially order m times f star, where f star is the max flow. Order m is to set up the residual network and to find the path, and it's possible that every time you may be just incrementing the flow by 1 unit, and so this is a sort of an ugly term in the running time, where the running time depends on the solution. So f star could be a huge number compared to the size of the graph, and so in instances where your capacities are very large, you don't want to run this algorithm. So Edmonds Karp came up with the following very simple idea to improve the running time to something purely as a function of n and m. N is the number of vertices, so always, and m is the number of edges. And their algorithm is simply always augment through shortest path. Seems very natural enough, and at least that bad example we saw will go away if you run through shortest path, right? That bad example of that recall this bad example where this capacity is 1, but this is some very large quantity. Then if you are not careful and if you use this middle edge all the time in your residual network, then you may be just incrementing the flow by 1 unit, whereas if you do just shortest path, one augmentation will get you this and another augmentation will get you this, and will be done, right? Now the question is, how do we prove? It seems very natural, nice heuristic, at least this example it works, but how do we in general argue that your algorithm will run actually in polynomial number of augmentations? So the running time we want to prove is some order. Okay, so we will, and the claim is maximum you will do order mn augmentations. And how much does it cost for each augmentation? M. Why? Right. So you, what does it mean by, what do you have to do for each augmentation? Once you have augmented it, the algorithm is the same as generic Ford-Fulkerson. Only thing you are doing is shortest path. So you augment and then go to construct your residual network. How does you construct a residual network? For every edge, if the edge is not saturated, you are going to add a forward edge with the residual capacity, and if it is saturated, you are going to, or if the flow is positive, then you are going to add a residual backward edge with that flow as the capacity, right? If the flow is non-zero, you will add a backward edge, and if the flow is full, then you don't add the forward edge. But if the flow is not full, you will add an edge in the forward direction with the residual capacity, right? This is exactly the residual network. So you have to look at every edge and do this to construct the residual network. And then what do you have to do in the residual network? You're going to find the shortest ST path. How do you find the shortest ST path? In general, in a undirected, unweighted graph, BFS, right? Good, right? At the end of third day, fourth day, at least you should be able to say this. So if you have an undirected, unweighted graph and you want to find the shortest path from a vertex, you just grow a BFS starting from that vertex. BFS has the property that the distances it finds are shortest distances, right? But if it is a weighted graph, what do you do? If the edges have weights, Dijkstra's algorithm you use, right? Because it's not, the shortest is not the length, but also adds the weight, so you need to do Dijkstra. So anyway, so if you just do BFS, in our case, we are only talking about, when we say shortest, it's only in terms of the length. Ignore the capacities, weights for the moment. You just find the shortest ST path. Once you find shortest ST path, whatever augmentation possible, augment it. That's the algorithm. So each augmentation costs you M, and we will prove that it will be Mn augmentations. So total runtime is order M square n. Okay, at least this ugly part about the flow value, output value goes away. It's just a pure function of n and m, simple polynomial function on n and m. So the rest of the lecture is trying to show this claim that if you augment through shortest paths, then the number of augmentations you will do is only order Mn, and we will prove two lemmas and then the rest will follow. After every augmentation, the distance, it is the shortest path distance d, I am going to use this notation dsv in the residual network never decreases. So increases or remains the same. Okay, what do I mean by this, right? So you have some flow and then you construct your residual network, right? So I start from S and here is a vertex V and I look at its distance from S to V in the residual network. Let's say that distance is some 5, okay? And then you augment again through the shortest path and you get another F prime, and in F prime, if you look at the length of the path from S to V, there may not even be a path, but the length of the path will never decrease. This path will either be 5 or more. That's the claim for every vertex. Okay, for every V in V minus S. Okay, so this is the first observation. More or less, this will help us to complete what we want to show, but this is very important. All we are saying is that the shortest path distance never decreases. And then we will show, I will write down the big picture and then we will get into the proof of these lemmas. Lemma 2 will say that every edge, okay, before that let us define a notion of a critical edge. in an augmenting path. So, an edge UV is critical in an augmenting path if UV is saturated, right, after the augmentation. Right, in my graph I call an edge, typically an edge in the residual network. It's called critical edge if in the augmenting path you are trying to find the shortest augmenting path, this edge after augmentation, this edge is no longer in the residual network, right, you have saturated the flow. Here is a simple observation. Every augmenting path has a critical edge, right? At least one. Agreed? Why? That's the way we augment it, right? I find a path. How much do I push it? The min in that path, that guy will be saturated, right? Because I am going to push whatever min residual capacity in that path possible. So that's all I can push anyway through that path. Once I do that, that edge which has the min residual thing will get saturated. So that was a critical edge. There may be several such edges. Many edges may get saturated. So a path may have many critical edges, but at least there is one. Okay. Now the lemma 2 we will show. An edge becomes critical at most n by 2 times. Recall the example we had, the small example we had, and let's look at the middle edge. How many times did it become critical? Every time, not twice, in every augmentation, right? You see, if I find this path, then that guy is the critical edge, so I will send as much as I can send. Then if I find this path, this edge will become critical again. So that edge is becomes critical f star times, and that was the problem which was giving me bad running time. But what we will argue is that any edge, so you may saturate it, you will send full flow, then you may decide to take it back and then send it again, but you won't do it many times. In particular, what we will argue is that an edge can become saturated, an edge can become critical at most n by 2 times. Okay, and I want to now argue that this is the end of the story. Is it clear? So if this is what is true, how many augmentations are possible totally? See, in each augmentation at least one edge gets critical, right? Now I am saying that if you look at all edges in the graph, any particular edge can become critical at most n times. So how many different augmenting paths are possible? M into n by 2, right? This edge may be critical n by 2 times, this may become at most n by 2 times, and in fact many edges may become critical in one augmenting path itself, but then that's even good, you will have fewer augmenting paths. So at most, right, because for every augmenting path at least one edge gets critical, another augmenting path at least another edge, and totally there can be m times n possible critical edges. So that will show what I wanted to show, that there can be at most order mn augmentations, and each augmentation costs me order m, so total running time would be m square by n, right? Okay, so now what we will show is these two lemmas, and these are just some routine calculations which will give you what we want to show. Okay, so is the big picture clear? The goal is, the idea is simple, just run through find shortest paths and augment, right? Seems very natural, you will think of it, you will implement it. But what we want to now prove is that this avoids all this pathetic case we had in that example of running time depending on the number of augmentations being that depends on the capacities and not just on n and m. We will argue that the number of augmentations is at most mn, and so the overall running time would be m square n. So these are the two lemmas we want to show. So after every augmentation, the distance SV in the residual network increases, it remains the same for every V. Okay. So let's try and prove. And we'll prove it by contradiction. Okay, so suppose not, right? So what do we want to show is that so here is your flow F, and here is my residual network, and later on another flow F prime after some augmentation in G F prime. Suppose in G F prime, that's residual network, the distance from S to V actually decreases, suppose. I want to arrive at a contradiction. This is what I claim that does not happen for some V, right? Right. The first lemma is crucial to prove the second lemma, which says that an edge cannot be critical too many times. That's the second lemma, and for that I want to show that first of all, as you do the shortest path augmentations, the shortest path distances are gradually increasing. Okay, they never decrease. Right. So eventually there will be a point that the shortest path distance will become like n, but that's not possible. So there won't be any path, and you will stop. Okay, that's a kind of an argument. So suppose not that there is some V in G F prime. So let's say this is my shortest path here in G F prime from S to V, and its distance actually has decreased from what it was in F. Okay, so this is my path, and let me also make one more assumption about closest to S in G F prime with that property. Sometimes this kind of thing is very useful for the proof that. So we are going to assume that is not the case. There is some vertex which violates my claim. There may be several vertices that violate my claim. Among all the vertices that violate the claim, I pick the one which is the closest to S, which has a problem, right? This is the problem. df prime SV is less than df SV. So what does that mean, closest? That means for U is actually greater than or equal to df SU, because otherwise I would have chosen U, right? U is closer to S, and that did not get violated. So that means at F prime, its distance is greater than or equal to df SU. Now I want to arrive at a contradiction. So let's capture again the picture. So I have F, GF, and F prime and GF prime, and in GF prime I have, and what do I know? What are the things I want to remember is that df. So this is a notation which I did not really explain, but hopefully it's clear. It is the length of the shortest path in GF from S to V is strictly more than in F prime, right? So because the path length has decreased, this is 1, but that's not the case for U. So df SU is less than or equal to Okay, now I want to get some contradiction. So let's look at the edge UV, right? So this is the shortest path in F prime. Let's see whether UV is in GF or not. So we'll have two cases. Suppose UV is an edge in the residual network on GF. Then I want to get some contradiction. So, I will try something and see if that works. So, in F, the length of the path from S to V then is less than or equal to, right. So, in F, suppose the edge UV was there, then the shortest way to reach from S to V may or may not through U, but if you look at the shortest path from S to U and you add 1, that is one way, but maybe it is even better. So, distance from S to V in F is less than or equal to distance from S to U in plus 1. Okay. Now, I want to just use some, sorry, because I am looking for a shortest path to V in F. So, one way to obtain a shortest path is to go from S to U, that will take me a distance of df of SU plus that edge UV, assuming UV is in the residual network. Okay. But why, you should ask why less than or equal to, all I assumed is suppose UV is in GF. So, it may or may not be. So, if the shortest path actually uses the edge UV, then it will be, the distance will be this, but it may not use UV and there may be a different way to get to V faster without U. So, it will be less than or equal to this. This is one path, so there may be something less than or equal to this. Okay. So, now I know from here that this is less than or equal to df prime SU plus 1, right, from 2. Okay. But in 2, this is the shortest path. We assumed in f prime this is the shortest path. So, df prime SU plus 1 is exactly equal to df prime SV, right. But I have arrived at a contradiction, because we assume that df of SV is strictly greater than df prime SV, but I just proved that it is less than or equal to. Clear? Some magic calculations happening, there is nothing much, but the important thing is to remember the shortest path keeps increasing. Okay. Oh, but this is under the assumption that UV is in GF, but maybe not. Maybe this edge UV was not in. So, okay. So, what did I prove? I proved that UV is not in GF, because I got a contradiction otherwise. Now, in this case also I will get a contradiction with this assumption, and then we will be done. So, otherwise, so what I have is this is the shortest path. So, df prime SU plus 1 is exactly equal to df prime SV, because in shortest path, this is the shortest path. So, it satisfies this what optimum substructure property, right. This shortest path plus 1 gives you this, and we have a contradiction. Okay, so let me just go back and draw this picture again. And so now through the contradiction, what did I conclude? That UV, this edge, which was part of the shortest path here, is actually cannot be in the residual network of GF, because with that assumption I had derived a contradiction. Okay, so what is, so this is my GF and this is F prime, and my shortest path in F prime uses this. And what are the things I assumed? That in F prime, the distance from S to V actually decreases from what it was in F, and U is not such a thing. So, df prime SU is greater than or equal to df SU. And now, through one argument, we already argued that this edge UV is not in GF. Okay. But wait, UV was not in GF, how did it get to F prime then? in the residual network. So, here is an edge UV which was not in the residual when we did the flow F, but somehow in F prime it got here. How? How is that possible? Very good. So, the edge UV was saturated and that is why it was not in GF, but in the augmentation you did, you pulled back something, right? You sent something through VU and so now it became into the residual network. So, that means in this path VU was in GF, okay, as UV is in GF prime, VU is not only in GF, is part of an augmenting path to get F prime. It is part of the shortest augmenting path. Why? Because we always augment through shortest paths anyway, right. So, VU is part of the shortest path. So, in GF, DF SU happens to be equal to DF of SV plus 1, as VU is part of the shortest path. So, this is an important argument and this is what we will keep using for the next lemma also. Now, I claim that I have some contradiction here and I should be able to get the contradiction, be done with it. So, what is the contradiction? Okay, so let me try. So, df prime or SU is equal to df prime SV minus 1, because this is shortest path. So, shortest path from here to here, this distance is this minus 1. Okay, let me write, this is 1, 2 and this is 3. Yeah. So, but df prime SV is strictly less than df prime df SV minus 1. Okay. But df SV minus 1 is nothing but df SU minus 2, because from 3 df SV is df SU minus 1. So, I have some contradiction here because I proved that df prime SU is strictly less than df SU minus 2, contradicting 2. I mean, I'd like to write it line by line, but this window is small for me. Okay. So, assuming if UV was not is in the residual network of F, I had some contradiction. If it is not there, then we argued that VU must be there for UV to get in the next augmentation. So, VU is not only in GF, but it is part of the shortest augmenting path. That gives me some equation based on the shortest path properties, and then I get some contradiction. But this is something, okay, so this is the end of the proof of lemma 1. What did I prove in the lemma 1? That my assumption that for V the path length decreases is wrong, right. If I make that assumption, then whether UV is in part of GF or not, I get some contradiction. So, this is wrong. So, for every V df prime is greater than or equal to df SV. Okay, so, the length of the shortest path from S to any vertex either remains the same or increases. Okay. In fact, this is a very useful thing which simply says that if VU was part of an edge augmenting path or in GF before, then the length of the path from S to U actually okay, no, so forget what I said. Okay, good. So, that actually proves lemma 1. So, what did I want to show? After every augmentation, the distance from S to every vertex remains the same or increases. So, we assumed that suppose not, and then we got some contradiction. Okay, good. So now let's get to, now I want to prove this next one, right. An edge becomes critical at most n by 2 times. It has a very similar flavor of the proof.